Good morning, everybody. And welcome back to Abstract Algebra. Plan for today is we're going to begin our discussion of Chapter 4 and start talking about cyclic groups. I've got my usual office hours this afternoon from 2 to 3, and tomorrow morning 10 to 11, tomorrow afternoon 1:30 to 2:30. Upcoming homework, if you haven't looked at it yet, homework 2 is posted on Blackboard and will be due this Friday evening. Homework 2 is kind of a little bit of a mix. It has a few kind of just computational problems, compute the center of this group, or the centralizer of this element type stuff, as well as a few more general proofs, like proving in any Cayley table for a group, each row has every element exactly once. So definitely recommend you start on that if you haven't already. Why is it not a good idea to teach horses analytic geometry? It's because you shouldn't put Descartes before the horse. Okay, so maybe questions or comments before we get started today, the new stuff. Okay, homework 1. I'm going to try and have homework 1 graded by tomorrow evening. We'll see if I actually get that done, but that is kind of the current hope. So you can have it to look off of before you have to submit the second one. But we will see. Grading these things takes a while. So this packet is going to last us like 3 or 4 classes. It's kind of a big packet, but today we're going to be kind of talking about examples of this new type of group, a cyclic group. And then we're going to spend a few classes proving a bunch of results that have to hold true for cyclic groups, ultimately getting to our first big name theorem of the semester, a fundamental theorem of cyclic groups. And that's where we're going to be heading over the course of the next week or so. So first of all, a cyclic group is a group that's generated by one element. Generated by a single element within the group. So you may remember we talked about this kind of in the first half of the subgroups packet. When we talk about a group being generated by a single element A, what we really mean is that every element in the group can be written in the form A to the n power, where n is A is just some fixed element. In G, and n is any integer, where you may recall we actually defined a to the n not necessarily to mean the exponential function multiply a by itself n times like you might be used to thinking about, but here we just mean a to the n in general is just going to be a star a with n copies of a, where if n is positive, this is how a to the n is defined. If n is negative, you just do the same thing with a inverse. And if n is 0, it's just a to the 0 we take to be the identity element. So basically, when we're saying a group is cyclic, that means that we can find some element, a in the group, such that everything in the group is of the form a squared, a cubed, etc., or is of the form a inverse squared, a inverse cubed, etc., or is the identity element. Given a group, if we can find some element A in the group such that everything in the group can be written in this way, we say that the group is cyclic. And if there is no such element A in the group, well, then the group is not cyclic. And we've seen lots of examples of groups so far, so I thought we'd kind of kick things off by me asking you to look at 6 different groups that we've seen so far. The integers, GL2R, the rationals, the reals, the non-zero rationals, and the dihedral group D4. And what I would like for you all to do is take a few minutes. If you want, if you feel comfortable, you can talk to the people sitting around you. And I would like you to see if you can determine if any of these groups are cyclic. And if so, which ones do you claim are cyclic groups? Go ahead and take some time and try thinking through each of these groups and see if you can determine if any of these groups can be generated by a single element.
Yes.
So,
I feel like
but our
this one's not gonna be this one is the fact that this will be. I agree.
So the inverse.
So for
Right,
fractions,
that's easy.
is that
Addition as well.
this one. If you do like.
I think so.
For
What is, it's a set of all, what we.
So keep in mind-
2 by 2 matrices?
That's what's making. So keep in mind, I didn't actually give you the group operations in any of these, because each of these only forms a group under one of these standard operations. But I will give you a reminder. The integers are under addition, GL2R is under multiplication, the rationals are under addition, the reals are under addition, the non-zero rationals are under multiplication, and D4 is under D4. Transformation composition. Fair.
I would definitely think it's a no.
Because it has 2 things you can do, you can flip it and you can rotate it. So it's only rotation.
You just, your intuition says no.
I don't like it.
Maybe it doesn't like you.
Imagine trying to multiply the same matrix over and over again to find any matrix.
I think, I feel like that's definitely not.
Wait a second,
Wouldn't
wait,
we just
you
be
want-
like?
what if your standard is
That's true.
rotate
And
and
then
flip?
real numbers don't just.
Can you rotate and flip and rotate and flip?
Well, it's the same thing.
I don't know. I don't know if it's possible. It's like running an experiment. You can always just,
Yeah, but like it's still.
It'll be awful.
yeah,
That would also.
because you're like flipping
Or does that
back
not
each
rational?
time.
But like, what would your number be?
Would you be able
Can't
to
choose
do that?
one.
Get all of them?
Yeah, no, for me, rational. So it's like, I would say it's just
There's
So,
some
like,
like,
yeah,
so
that's
every
what
occasion
Yeah.
that you couldn't get to
Like,
five
or like,
different
like,
combinations
like,
of
rotation.
rotations, but then you can get
For real, so like, never get into decimals.
So I can sit down.
But you need decimals when you're doing the.
Okay, so it is.
I
Same
rotate.
with the rational, right?
Because you can't, you would have to take either just like.
No, that's exactly where you started.
Oh.
Because you flip and rotate. No, because rotating twice.
Said no,
Rotating twice.
But not
Rotating
one
3 times. Probably the same.
What about the multiplication one?
That's under. I don't think it works.
The multiplication for.
But I wouldn't
Yeah.
be surprised if I was wrong.
That makes that, you know.
Right.
It makes all the difference.
Okay, how in the world do we get all the real
That's
numbers
not the
from
form.
under addition?
How would D?
That
So,
would be.
could everything be
Isn't
derived?
that for complex numbers?
The thing.
Q
Rational numbers.
is rational, so just
Right, I need something that's
Like I
infinitely
believe
small,
that's
right?
Right.
Yeah, because it keeps getting.
So,
Right.
because you guys are just are like the fractions. So like, you basically keep
No,
going like infinitely small. Like,
Okay.
you like 0.0000, but then how do you get big, and then you can like.
What about the
If it's
rest?
under
There's some
addition.
sort of
I
weird-
think it's not. You can do
It's
that.
under multiplication.
I guess that you can.
Oh, you
for
for Q star, yeah, so it's
But it just means one. I think the problem is that that's not rational numbers, you can.
No, because if you were doing under multiplication, then it would be the big one.
If you have one.
Yeah, but not zero.
The inverse is.
What do you
Now,
is
do you need
one.
For the.
So that's why you can.
So a generator
Maybe
is
that's
just
why.
a single element that will
Right.
create
You
multiple
can
volumes.
make fractions.
Well, we could do it with
Yeah.
someone.
No, I don't think it's like.
Wait, it's
So
to
it's why we're
to
doing it.
negative power, right? If we had.
So is that gonna be a no for both of you?
Sure, so that will give you,
Because this
it's
one is
not be a generator of integers because two That will generate all of the real numbers if you add it to itself over and over and over and
Is there
Maybe
Yeah,
it's
really
easy
something else?
Yeah, that's what I was thinking.
Over and over
I don't
again.
like
How many
that.
but I cannot.
Do they
Under that.
So I don't think one will
Get
generate.
under addition either because once again, our thing has. to
So wait,
use-
those two are the-
Oh, you think
It's not a single.
Right.
That's the sort
What
of
about
mindset.
GL2?
So without
That's tricky.
Why would
Because it's weird because you have like at least two entries, right? So.
as many
Yeah,
parts
those
as
two areas
possible.
are just
So zero?
They just keep adding it to itself.
No.
So you just keep adding zero to itself over and over.
You saw that.
That's the only way. You can never get
Oh.
Right.
Oh, I forgot, yeah, you changed, I forgot these numbers.
Alright, yeah, right.
Right, so you want to are multiplications.
I know, the first one was so fun, I was like, oh,
You can
yeah.
just.
After that, I was like, now I'm just hurting my head.
You only found one.
Yeah, teacher.
I mean,
No, it's
that's
just.
the,
You want to like bar
which
X.
is what.
Right,
It's
and
like,
then like throw zeros
That's
and
what's
one.
like down every
We're really trying to find another Dr. G.
You didn't find any more than one.
Listen, this is.
Unless I mean, there only is one.
I know, it's like he could, it does seem like a thousand years He said Elaine is not gonna like this. And then did it.
Let's do
Oh.
it.
How would you-
What if they're all?
Wait a second,
Say
wait,
E3 would be.
Do the entries have to be a set of real numbers?
So that's what flip back into
So
work
this
every.
So then
like,
real
Yeah.
numbers. That's not what happens.
It's gonna be like one full cycle.
C is
of
not,
every
everything
second.
else is.
Can you do one of these cycles? What's the
I'll give you a hint. Let's see. People who've taken real analysis, here's a hint.
Yeah.
Cyclic groups can only be countably infinite at most.
That's what I said.
And did we figure out,
That might help him knock out a
well, I thought we were.
So, I said-
We couldn't really get
Real
numbers
numbers
or
are
not.
not. Yeah.
Yeah, well, like fractional numbers too.
What?
You have to do like, yeah, every,
Yeah, can we get?
it's like a little spiral,
Like
it
what
goes to
about
every
one
single
third?
fraction,
That's
and
real
you have to
numbers.
divide them up
Yeah.
with.
It's one of the things I would talk about in discrete that I had another one.
But you can't do it for R.
Yeah.
Right?
So that you can.
So that just rules out R.
Well, that's.
No, that rules out another one.
That doesn't work because it doesn't have enough numbers.
So at least you don't deal with that.
Alright, so if the idea
This is a no, this is a no.
So,
So the key.
For a cyclic group,
we need something that's
does it
like,
just have to be like, a to a certain number?
Yeah.
Can I say do
Hey,
a
do you
squared
no, not the normal range.
You gotta keep in mind, you only have a single operation here, which is whatever star is your group operation. So you can't really say a squared plus a to some other power. At least not until we get to rings, and that won't be until the second
I
half.
wanna say no, but, so, but only.
Rings are like groups that you have two operations instead of one.
What's that?
I don't
Yeah, know, right? You make us think about
Well,
all
it's
these.
tough because we're gonna talk about the last like 4 weeks.
Great, thanks, Dr.
Just
G.
feel like
Alrighty.
it's gonna be really
You've all had a chance to think about these for a few minutes. So, kind of like to go through and just hear your all's thoughts on which of these do you think are cyclic, which ones do you think are not cyclic. So how about the integers under addition? Does anybody, so I see a lot of thumbs up, so it sounds like you all were able to maybe find some integer that generates the whole group. So, what would be an example of an integer that would generate the entire group of all integers under addition? Okay.
1.
1. So Cowley's claim is that if we take the group generated by 1, it'll give us the entire group of integers. And I agree. Because if you were to take 1 and add it to itself over and over and over again, that would give you every other positive integer. If you took the inverse of 1, which is negative 1, and added itself to itself over and over and over, that would give you every negative integer. And if you just took the identity, if you tacked on the identity element, which is 0, that's every integer. All the positives, all the negatives, and 0. Yes?
You said we could use integer powers, right? For the n, right? For n.
Well, keeping in mind that in this case, since our group operation is addition, when we say like 1 to the n, we mean 1 plus 1 plus 1 over and over. Taking to a power is the notation we use, but it doesn't necessarily mean that based on the group.
So you couldn't say like, you have to use the inverse to a power instead of saying a to like a negative power, that being to subtract this.
Well, in general, if we take a to a negative power, we just mean do a inverse with itself, positive n times.
Got it.
That kind of accounts for what does it mean to take a negative power of an element here. Anybody find any other generators for the integers?
-1.
-1 will also generate the entire group of integers. Fun fact, in any group, the group generated by G will always be equal to the subgroup generated by an element G will always be equal to the subgroup generated by G inverse. Why is that? Why would G and G inverse always have to generate the same subgroup?
Because G and G inverse are always together. I don't know how to explain it, but like, never mind.
Huh? Yeah, I think you're onto something. They're always together.
Like, well, if you have like G, then like G inverse is like a part of that. And if you have G inverse, then like you can start at like G times, because I don't know words.
Words are hard to come by. I think you're on the right track though. Lane?
Okay, so if you have the group generated by G, you've got G to all the negatives, and those just become G to all the positives when you go to the inverse, and the G to all the positives go to the negatives, and the identity element is still there.
Yeah, basically it comes down to the fact that the group generated by G will contain all these powers, positive powers of G, and the negative powers of G, which are just powers of G inverse. If you start with G inverse, then all the positive powers of G inverse will just be the negative powers of G. And then if you take G inverse inverse, that'll just take you back to G, so that the negative powers of G inverse become the positive powers of G. So since 1 and -1 are inverses of each other in the group of integers, they're going to generate the same subgroup, which in this case happens to be the entire group of integers. And I do believe 1 and -1 are the only integers that will do that. But both of these will work as generators of the group of integers. How about GL2R, the multiplication?
I want to say not cyclic because in my memory from linear algebra, I feel like GL2R includes the matrices that are like linear independent vectors. They have two linear independent vectors, and I don't think any one matrix would be able to get all of those, I guess.
Yeah, I think that's a good way to describe it. So one way you could describe it is by just saying no single matrix will give you will generate a group that contains both of these two things. Because anything that to a power will give you the identity matrix will not give you this thing to any power. How about the rational numbers under addition? Except all fractions. bunch of head shaking. Turns out this is not a cyclic group. And here's your proof. I'll have the real numbers under addition. Nope, for similar reasoning. Non-zero rationals under multiplication. Finally, how about D4? Well, D4, there's only 8 elements. We can actually check. We can actually brute force just check all 8 to see if they generate the entire group. So, we look at the subgroup generated by the identity element. How many elements are going to be in that subgroup?
1.
Just the identity element. We look at the subgroup generated by a single rotation. So these are rotations on a square, so 90-degree rotations. We're going to get R. We're going to get R squared. We're going to get R cubed. We're going to get the identity element. And I think that's it, since the inverse of R is R cubed, and vice versa. R squared and the identity are their own inverses. So R isn't going to give it to us. R cubed is going to turn out to generate the same thing, the same group, just the group of all rotations. R squared is just going to give us the identity element and R squared. Because R squared is its own inverse, and if you just multiply or compose R squared with itself a single time, you're going to get to the identity element. What else we got? We got S. Well, S is an element. That's a single reflection. That is its own inverse, which means it's just going to generate itself in the identity. We can check RS. Well, that'll just generate itself in the identity, since RS is its own inverse. We could try doing R squared S, which happens to only generate itself in the identity. And finally, we can try R cubed S, which also only generates itself in the identity. So that by brute force, D4 is not a cyclic group because we checked literally every single element in the group. None of those elements generate all of D4. By the way, while I have all the subgroups of D4 up here, because it turns out these give us all the subgroups. Anybody notice anything about how many elements are in each of these subgroups? Anybody notice a pattern? Let's see, this one, these two have 4 elements, 1 element, 2, 2, 2, 2, 2. And D4 has 8 elements. Anybody notice the relationship between 1, 2, 4, and 8?
1, 2, and 4 are all factors of 8.
1, 2, and 4 are all factors of 8, meaning the size of each of these subgroups is going to be something for which 8, the size of the entire group, is a multiple. Coincidence. Turns out the answer is no, but we're not going to get to that for a while. Yes. So yes, turns out out of all the groups that we've seen so far in this class, only one group, the integers, is cyclic. Technically we could say NZ is also going to be cyclic for any n, which is the set of all multiples of n under addition. But those are all just subgroups of the integers. We haven't seen any examples that don't involve just the integers under addition yet. that are examples of cyclic groups. That's what we're going to be trying to develop for the rest of class. It's kind of a couple of other examples of some cyclic groups. Yes?
Would D3 be cyclic?
Ooh, D3. Oh, you make me do this again?
Yes, please.
All right, D3. Then the element only generates itself. R and R squared, I think, will generate the same subgroup, which is just all of the rotations. So here, remember, R cubed is the identity, because R and R squared are inverses of each other. Here, if we take S, we're going to get just the identity element back and S. If we take RS, I need to do some math. RS squared again, that's going to be R times R squared S times S squared times S, that's the identity. And if we take R squared S, sorry, that Hegel group doesn't work either. No element generates all six. Though I will notice, mention, subgroup of order 1, order 3, order 2, order 2, order 2. Once again, the order of all these subgroups is dividing the order of the group at large, which is 6. Because 1, 2, and 3 are all factors of 6. Gadzooks. We're going to have a theorem later in the semester called Lagrange's theorem that says this has to happen for every group, by the way. So what I want to do for the rest of class is to talk a little bit about some modular arithmetic. Is anyone, out of curiosity, is anyone taking number theory here? I've got one. So this is kind of so the examples we're going to be looking at for the rest of class are going to be ones that show up in number theory a lot. And in order to do that, we're going to have to talk about how you do long division with remainders and quotients. Everyone remember doing that at some point in their lives and how exciting it was? So this is going to be an example that will generate some cyclic groups for us. So I'm on the second page, and it comes down to this theorem that tells us that's basically the Euclidean algorithm theorem, which basically says, given any integers a and b, there exist some unique integers. I don't know why I said some. There exist unique integers Q and R such that A is equal to QB plus R, and R is going to be between 0 and B. So given any two integers A and B to start with, there exists going to exist unique integers, a unique pair, Q and R, such that A is equal to Q times B plus R, and R is some integer between, that could be 0 at its smallest, and at its largest is going to be absolute value B minus 1. We're not going to prove this now. There's a proof in chapter 0, I believe, of the textbook. And a really formal proof gets into a lot of ring theory, which is something we haven't talked about yet. But this is going to be something we use to actually describe a group. So let's do a few examples of this before we, just to see if we can convince ourselves why is this theorem going to be true. So let's say we had A equals 17 and B equals 5. I want to be able to say 17 is equal to 5Q plus R for some R that satisfies R is between 0 and the absolute value of B is 5. How can we find what would be the unique pair of integers Q and R that would satisfy this equation? That 17 is equal to 5Q plus R, and R has to be something between that's greater than or equal to 0 and strictly less than 5.
And Q equal to 3 R equal to 2.
2 equals 3, r equals 2. I like it. It's the only pair of integers that'll get the job done. How about if a is equal to 2 and b is equal to 7? That would mean we're solving 2 equals 7q plus r. R has to be something in between 0 and 7. What could our q and r be that would satisfy this equation? Keep in mind, q can be any integer that would make this work. It's only r that has the restriction of it has to be between 0 and our value of b. Yeah, fine.
Q is -1 and R is 5.
Q is -1 and r is 5. So that'll give us 7 times 1, 7 times -1 plus 5. Is that going to give us positive 2?
No.
Don't think so. Okay.
0 and 2.
I think that'll work. If we let q just be 0 and r be equal to 2, and then r is between 0 and 7, and it also satisfies 2 is equal to 7 times 0 plus 2. If we do one more example, here we'll get negative to make Elaine happy. What if our a is -16 and our b is equal to 6? Meaning we need r to be between 0 and 6, and we also want q and r to satisfy -16 is equal to 6q plus r.
-3 and 2.
Let's see. If we let q be -3, then 6 times -3 is -18, plus 2 is -16. And 2 is between 0 and 6. Yeah, I think that checks out. Anyone want to take a stab as to guessing why did we call these two other integers q and r specifically? There is a reason.
Quotient and remainder.
Quotient and remainder. Bingo. It's because way back when you were wee lads and lasses, when he tried to take 17 divided by 5, he said, it's 3 remainder 2, because our quotient is 3 and our remainder is 2. So the fact that this theorem exists and tells you you can find unique integers q and r that satisfy this relationship is really just boiling down to the fact that it's saying there's a unique quotient and a unique remainder when you do long division of integers like this. I'm guessing you probably didn't in grade school try and do long division with -16 divided by 6. Getting things like, oh, it's -3 remainder 2. But you could. And this would kind of be the general process. Or 2 divided by 7 is 0 remainder 2. You're going to define a binary operation on a set of integers. That's basically going to be a star b is equal to r. I need a better piece of chalk. Got out a bunch of good pieces of chalk this morning, and then Dr. Murphy used them all up. So here's our new binary operation. So Q we're going to call the quotient. Oh, I forgot I put that in actually in the packet. R is the remainder, we're going to be the remainder in this expression. And we're going to define A mod B is going to be something that we're going to define to be equal to R, where R is just the given remainder term that's guaranteed by this theorem. It's going to be the remainder term, and we take A divided by B if we were to do long division. Mod here Dr. Gerstle, that's not a mathematical operation, that's a word. Well, it's a word used to define a mathematical operation. Just like if I say 0 plus 2, I could write out 0 plus 2 in the same way. Mod is short for modulo, which itself is short for modular. And doing this sort of math with like long division, finding quotients and remainders, we're calling modular arithmetic. So mod is short for something, which is short for something, which is short for something. And according to this, as an example, how would we find 17 mod 5? What?
Divide 17 by 5 and then subtract.
So that's going to give us 3.
Times what you got.
So that's going to give us 3. What would our remainder be?
Multiply the 3 times 5 and then 17 minus 5. Just 15 is 2.
It's going to be 2.
That was a lot of steps in my brain.
That was. How about 2 mod 7? Okay. It's going to be 2. And how about negative 16 mod 6? I'm not sure if I've looked at the other board enough times.
2.
It's going to be 2. How about that? It's 2 in everything. Example. That was not intentional. But that comes from the fact that we've already computed this. It's just the R that we found earlier, in that if A is 17 and B is 5, the Q and R that satisfy this theorem is going to be Q equals 3, R equals 2. So that R being 2 told us that 17 mod 5 had to be 2. Here, if A is 2 and B is 7, that gave us a remainder of 2, so that is going to come out to 2. Negative 16 and 6, the Q and R we found was Q is negative 3, R is 2, so that R comes out to 2. Whoa! You just did that mentally? 1 gajillion divided by 3 had a remainder of 1? How did you know that?
Because with 3s you can only ever get up to 9999999 up to whatever one less than that is.
That's exactly right. Since 1 bajillion divided by 3 is going to have a remainder of 1. Because we know if we subtract 1 from all this, we're going to get something that is a multiple of 3. And if you add 1 to that, it'll get you to the 1 bajillion. 1 less than this is a multiple of 3 because 1 less than this is 999999999. And anything with just a bunch of 9s in it is automatically a multiple of 3. Pro tip, if you want to find out if a number is a multiple of 3, add up its digits and see if that sum is a multiple of 3. So let's do a little bit simpler one. Is that a multiple of 3? So here's a tip. One way you can do this modular arithmetic, if you want to find 91 mod 4, add or subtract 4 enough times until you eventually get something within this interval. So basically, if we want to find something like 91 mod 4, we can just add or subtract, in this case subtract 4, keep subtracting 4 over and over again until eventually we end up in our interval between 0 and, in this case, 4. Alternatively, see, what is the multiple of 4 that is next smaller than 91, and then just add upwards from that? Oh, did you have your hand up?
No.
Unfortunate for you. 88 would be the next smallest multiple of 4. Which, by the way, if 88 is a multiple of 4, if we were to take 88 divided by 4, what would our remainder be? So if 88 mod 4 is 0, what's 91 mod 4 going to be? It's going to be 3 more than that, because 91 divided by 4 is going to have a remainder of 3. 91 divided by 4 will have the same quotient as 88 divided by 4. These would produce the same q's, but this one just happens to have a remainder of 3, while this one will have a remainder of 0. And so 92 mod 4 will have a remainder. If we just go up 3 to get from 88 to 91 mod 4, then we can just go up 1 more to get to 92 mod 4, so that 92 mod 4 is 4, right? No! It's 0. We have to wrap back around again because we just produced another multiple of 4. And so this is kind of our way of basically being able to do this modular arithmetic. You could do this with negative integers too, like we did here. We generally don't. We're not really going to very often. But this process works just as well in reverse with negative integers as it does with positive integers. So there's a binary operation for you, A mod B. Let's do another one. So I'm going to flip the page. We can actually define what it means to do sums, differences, products, modulo n. In general, given integers a and b and n, we can define a plus b modulo n, which you often read as just out loud as a plus b mod n, where here, the plus, we're just writing a little subscript of n on the plus symbol. And what this means is it's just going to be defined to be, you take a plus b normally, and then you mod out by n. Alternatively, you could also do a mod n plus b mod n and then mod out by n. It's pretty weird. Let's do an example of this. Let's say we wanted to look at 7 plus 12 mod 3. Which, if we wanted to, we could write it like this. 7 plus with a little 3 on it, a 12. We have 2 ways we could work this out. We could add 7 and 12 normally, and then mod out by 3, which would give us 19 mod 3. And if we were to take 19 divided by 3, what would our remainder term be? It's going to be 1. Or we could do 7 mod 3 plus 12 mod 3. What's 7 mod 3? 7 divided by 3 is 2 with the remainder of 1. What's 12 mod 3? 12 mod 3 is going to be 0, since 12 is a multiple of 3. 12 over 3 is quotient 4, remainder 0. We'll get the same thing. Turns out, if you want to take mod 3 at each step, and then keep it, and then add, if you want to take both numbers mod 3 and then add, you can do that. Or you can just add normally and then do mod your answer at the end. It'll always get you the same answer every time. Proof of that to follow when we talk about quotient groups later in the semester. Question?
can you split it up too? Like, can we have 19 mod 3 and just be like, what if we want to make it 7 plus 12 mod 3?
Sure.
Cool.
19 mod 3 is equal to 7 mod 3 plus 12 mod 3. So if I gave you this expression, if you'd wanted to, you could have found that by saying, I'm going to find 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 mod 3 plus the same thing again mod 3 if you really wanted to. I'm going to take a stab and say this is equal to 1 mod, this is going to be equal to 2 mod 3 right here. Which, if we take that mod 3, we'll get 2 mod 3. And then we'll have to add another copy of 2 mod 3. And what's 2 plus 2 mod 3 is going to be 4 mod 3, which will give us 1, and give us the same answer as this one. You can mod it, you can split something up and mod as many times as you want along the way. You should always end up with the same answer, no matter what your process. There's no way to split this up in any way that'll eventually get us to a final answer of, say, 2 or 0 mod 3, so to speak.
In your example, is there any way we know that both 7 and 12 are being modded by 3 and not like 7 plus 12 mod 3?
It comes from the fact that, like, when you say something like, oh, I gotcha, here parentheses may be useful. I maybe should have made it more clear by saying that. In general, you're never going to encounter a scenario where you have 2 numbers, one of which you're going to mod out by, say, 3, and the other of which you aren't. But you're right, I should have maybe done this to make it more clear. If you ever see this sort of notation, then that makes it clear that everything is being modded out by 3. That the addition operation you have is addition modulo 3 to everything. Do the same thing with multiplication. A multiplied by n, a times b mod n, is, you can also do as either a times b mod n, or as a mod n multiply mod n, but of course by b mod n. So if we had, for instance, something like 5 times 6 mod 4, we could do this in a couple of different ways. We could multiply 5 and 6 together, which will give us 30 mod 4. And if we were to take 30 divided by 4, what's our remainder? It's going to be 2. Or we could take 5 mod 4, multiply it by 6 mod 4. Let's see, 5 mod 4 is going to give us 1. 6 mod 4 is going to give us 2. And when we multiply 1 and 2 together, mod 4, it will also end up with 2. So multiplication and addition are both going to work the same way. All right, I got 2 minutes. Here's the punchline for addition. We can form a group of integers under addition mod n for any n. And I'll leave you this to chew on for Friday's class. If we define z slash nz, I'm going to explain the notation in like a month from now when we're using it to mean other things. I'm just going to define, this is going to be read out as z mod nz, which we're going to define to be the set of integers from 0 up to n minus 1. If we take this set of integers, mod n, is taken under addition mod n, it's a group. Not only is this going to form a group, it's going to give us another example of a cyclic group. Our first example, in fact, of a finite group that also happens to be cyclic. Gadzooks. I'll leave you with that thought. When we come back Friday, we'll talk about Z mod NZ being a group under, cyclic group under addition, what that means. And then we'll also talk about under which circumstances does Z mod NZ form a group under multiplication mod N. Spoiler alert, sometimes it does, sometimes it doesn't. Good day, everybody.